All right, in section 5 today we're going to talk about measurement variation and different distributions. Today for this you only need your note packet and a pencil. When you have those two things ready, go ahead and continue on through the video. So getting started today, the first definition we have is measurement variation. This is when you measure the same thing over and over again but get different results. And we've seen this in class during this unit. I'm sure you've seen this in class in another science class if you've been doing experiments. And so most people will contribute measurement variation to human error. So when you are timing, like on the stopwatch, human error can be measurement variation. So you should be getting the same thing over and over again, but you don't always. Okay, so when you're trying to get 5 seconds on a stopwatch. Luck or chance. In the penny flip experiment, every time you flip a penny, you should have a 1 out of 2 chance of getting a head or 1 out of 2 chance of getting a tail. And so every other time you would hope get heads, tails over and over again. As you know, that doesn't happen. But if we repeated this over and over and over again, they would eventually even out with more and more results. So luck or chance can be measurement variation. So you should be getting the same thing over and over again, but you don't. And then the third one is environmental variation, like in the pulse experiment. So sometimes environment can play an impact in not being able to get the same results. So in pulse experiments, you're trying to calculate your pulse several times in a row. We weren't getting the same number over and over again. So could be a little bit of human error in that as well as counting, but your heart rate, the environment around you, could make your heart rate change. And so there's other scenarios where that would happen. So again, a perfect scientist or a perfect condition, we want to be able to get the same results over and over again, and sometimes you can't. And so we'll talk more about measurement variation as we go through class. So it's not just human error, but there's other things that go along with it. But that is the most common reason for not getting the same results over and over again. So moving on to distributions. A distribution is the way a set of data is spread out. There are many types of distributions, but today we're going to focus on a few well-known types. So when you think distribution, you can think of a histogram. What does this data look like graphically? So the first graphical representation is the normal distribution. It has the bell shape, so it's the tallest in the center, symmetrical. We have lots of details about the normal distribution, and we'll look at those details when we get to the end of this note guide. So normal distribution, that's the histogram that we're really going to be looking for the rest of the unit. Left skew distribution, that's when the tail of the distribution is pulled off to the left. And so it's also known as a negative skew. And so when the taller bars are on the right and the shorter bars are on the left. So notice it says the tail is pulled to the left. So this is called a negative or a left skew. It's kind of the opposite of what you think it might be, but the tail is where you talk about the skewness. And then the opposite of that is a right skew, also known as a positive skew. That's when the shorter bars are on the right. So heavy concentration, lots of data over here. This is where your mode would be at. The most common numbers is where the tallest bars are going to be. And that's the same here on the left skew. This is where the most common frequencies are. There's different data sets that would produce histograms that look like this. The fourth one is random. When there's no pattern, the bars are all different heights and kind of scattered all over the place. Sometimes when you just have a little bit of data, your histogram can kind of look random, but as you get more and more data, it might start to take the shape of one of the first ones we saw. And the fifth one is a uniform distribution. The frequencies are all about the same. A good example of this is when you are doing an experiment and all of the opportunities for results are equally likely, when the likelihood of the events are all equally likely. For example, when you're rolling a dice, you have 6 sides. 1, 2, 3, 4, 5, 6. Every time you roll the dice, you have the same opportunity to roll a 1, a 2, a 3, a 4, or 5, or a 6. And if you keep rolling that dice over and over and over and over and over again, you should have 6 bars, all about the same height, because all of them are equally likely, uniform, when the bars are the same height. Okay, so on to normal distribution. As I said, there's lots of details about normal distribution that we want to be familiar with. And again, this is a bell shape. The tallest bar is in the middle, and it gradually lowers on both sides, which again means this data is symmetrical. Very few data sets have perfect normal distribution in real life. So when we have these experiments, very few are perfect. However, if it does have a perfect normal distribution, this is pretty awesome. The mean, the median, and the mode are all going to be the exact number. And graphically, I want you to look at this bell curve down here. This normal distribution, where would those 3 numbers be? The mode is where it's most common. The mean and the median, they are all going to be this number right here in this center bar. That's where those are at, okay? If the data set is almost a normal distribution, the mean, median, mode will almost be equal. That means that they might be, let's say this range here of this middle bar is from 50 to 53. One of them might be 50, one of them might be 50.5, and the other one might be 50.2. So they're all going to be approximately equal, but not the exact same when they are approximate normal distribution. So that means that these bars won't be perfectly symmetrical, but almost. Now I need you to be careful. You might look at a data set and calculate the mean, median, and mode. They might be the same. It does not mean that you will get a perfect histogram. Okay, so if you have a perfect histogram, you can conclude that you have the same median, mean, and mode. But if you get the same mean, median, and mode, you cannot conclude that your histogram will look like this. And we have a couple examples of that in class. One of them is like a trimodal histogram. And that looks like, so I could look at a data set and get mean, median, mode all the same, and I could, however, get a histogram that instead of having one tall bar right in the center, you might have a tall bar here, here, and here, all the same height, and then it staggers down lower, and then it staggers back up higher, and then comes off lower again, and then comes down lower, and then gets higher, and then back lower. And so there's really like 3 bell curves in this data set. Okay, and so that's just one example of when you can get the same mean, median, and mode, but this is not what the histogram will look like. Okay, and then lastly here, data might not seem normal until you get a lot of results. For example, when we looked at the flip-flip, one person's flip-flip data might have looked random, but when we get the whole blue team, all 100 pieces of data times 10, so all 1,000 pieces of data put in there together, we can get our normal looking curve. That concludes our distribution notes, and we will again can continue on with distributions and really focus on normal distribution as we go through this unit.